Let me start with a small erratum. So Choyu pointed out, asked me yesterday a question, and I said, I don't know how to do things on the board because it's, well, board pressure. But actually, the problem was much deeper than that. It was that I actually had a false statement yesterday on the board. So I had a theorem or a fact, I don't remember, that said that if W is negative definite, and it's a cobordism between two homology spheres, then F infinity W S is an isomorphism for every S spin-C structure on W. This is actually false as stated. So one needs an extra assumption, namely that B1 of W vanishes. And the example that you might want to think about is what happens when you take S1 times S3 and you remove two fourballs and view this as a cobordism from S3 to S3. And you can check, just for degree reasons, that this map has to vanish. Or you can take a handle decomposition of that cobordism, which consists of one handle and two handles. And this is the perfect case where everything is formal. You don't have to do any triangle counts. There are no holomorphic curves involved. And you can just compute everything just formally and show that this map vanishes. So no panic, no reason to panic, since in the argument what I said was, oh, I have a cobordism that's negative definite, so it induces an isomorphism, and I can suppose that B1 is 0 because I can surger it out. Instead, I just invert the two steps. I surger the B1 out, so I have now the assumption B1 is equal to 0, and then maps actually do induce isomorphisms on HF infinity, and then the argument that I had yesterday just goes through, more or less unchanged. Things do not commute, but if you do them in the right order, things work. So thanks to you. And this is when you read something that you really trust and you really want to be true, and you don't question what you're reading, or you don't question what somebody is telling you. And the moral of the story is you should question what people write. Especially certain people are known for not writing very, very well and very, very carefully. But yeah. Anyway, this is recorded, so I won't name names. So today, I had promised the Thom conjecture, and I think I deliver, well, partially deliver. So what's the context? Let's recall. Probably most of you are familiar with everything that I'm going to say for the next 15 minutes. CP2, the complex projective plane. This is defined, well, algebraic geometers like to define it as C3 minus the origin modulo the action of C star. This action is the diagonal action, so lambda of x, y, z is equal to lambda x, lambda y, lambda z. We topologists prefer compact spaces, so we just take the unit sphere and mod out by the unit sphere. This representation has the advantage of working with compact things, so this is obviously a compact space now. This has the advantage of, well, actually what you get is a complex surface. So this is perhaps the simplest complex surface. It's uniquely characterized by the fact that it's simply connected and that B2 is equal to 1. Let me say plus projective. No, actually you don't need that. It's also characterized by the fact that H1 is trivial and B2 is equal to 1. It's not characterized by the fact that B1 is 0 and B2 is equal to 1. For people who care, there are objects called fake projective planes that pop up, but yeah, I don't want to talk about that. And in a complex surface, we have lots of curves. And word of caution, there are complex surfaces lurking around, complex curves lurking around. I tend to mix up the two terminologies, so I tend to call curves something that is actually a Riemann surface, and I tend to call surface something that's actually a four-manifold. So if you get confused at any point, just shout out and say, please make up your mind and tell me which objects you're talking about. So in CP2, there are complex curves. These are 0 sets of homogeneous polynomials. 3 variables. And if you're not unlucky, meaning if you choose a sufficiently generic polynomial, then this 0 set, so most of the time, this yields a smoothly embedded surface, oriented surface. This is one of the cases where not being unlucky actually means that you can give concrete examples. So you can look at Fermat curves. These are defined by the polynomial x to the power d plus y to the power d plus z to the power d. This is a degree d curve. The claim is that this is smoothly embedded. That for d equal 1, so this is a case of a complex line, we get a generator of H2 of CP2. And in general, and that this is a two-sphere. Topologically, a complex line is a Riemann sphere, which is a smooth two-sphere. And in general, maybe let's call this CD, FD for Fermat. In general, FD is an oriented surface of genus d minus 1, d minus 2 divided by 2, which lives in the homology class d times the homology class of F1. And if you were in Montpellier in February, you've heard a lot about these things from me. If you are not, well, too bad for you. And it was a long-standing question for maybe almost 40 years. So the question, are there surfaces in CP2 that have smaller genus than FD, but lie in the same homology class. This, well, actually, I can phrase this a bit better. I can fix more generally. If I have a four manifold, closed, oriented, smooth or not smooth, doesn't matter at this point, and I have a homology class, then I can ask what is the minimum among the genus of all surfaces that are in the homology class. And I call this the genus of the class A. And the question is, if I pick X to be CP2, and if I pick A to be some positive multiple of F1, is the minimal genus attained by a complex surface? So the Thom conjecture was that the answer is no, you cannot do better than this. And this turned into a theorem due to Kronheimer and Mrovka. In '94, very good year for four manifolds. This was known as the Thom conjecture. I can state it using this language, that G of D times F1, and oftentimes I will just call this homology class H, H for hyperplane, and not for line, but yeah. Is equal to D minus 1, D minus 2 divided by 2. Or equivalently, maybe more poetic way of phrasing it is that complex curves are genus minimizing in their homology class. So the way I stated it is only for CP2 because, well, I am choosing a generator. You're leading to the third remark that I wanted to do. Yeah, let me do them in order, and then second remark actually. So the first remark. Say it again. Yeah, the problem is a lot more general. It's known as the minimal genus problem. But the question that I stated and the conjecture were only for CP2. But we're going to get there. So the first remark is that Kronheimer and Mrovka's proof used Seiberg-Witten theory. And the proof that we're going to see today, hopefully, is due to, well, guess who? Poschwart and Szabo. But their proof is inspired by what I think is more or less the same proof, by an analogous proof in cyberalgorithm theory, which is due to Sachos-Trellet. Just a couple of years before they did this. And let me just point out a corollary to the theorem. The corollary is the Milnor conjecture. If you don't care about surfaces in four manifolds, which you should care, but if you only care about knots, for instance, you have the unknotting problem for knots, and you can ask, well, if I give you a knot, what is the unknotting number? And the corollary of this fact is that the unknotting number of the torus knot TPQ is what you expect it to be. It's the same as the cipher genus of the torus knot. And actually, this turns out to be a consequence of the fact that the slice genus, which I'm not going to define because I don't really care right now, is a half P minus Q. And all these things are related. So now, Gregor's question, it's a very good question. In general, if X is a projective surface, and C is a complex curve, then it's true that C is genus minimizing. In its homology class. And I think that this is due to combined work of Cronheimer, Mrówka, Orzbat, and Szabo, with, I guess, input from Morgan and that's it. There's the Morgan, Mrówka, Szabo paper that I think is entirely short. And actually, slightly more is true. This is true for Kähler four manifolds and for symplectic, well, actually for symplectic four manifolds and for symplectic submanifolds. So there's generalizations to this. And the third remark that I wanted to make is that you should have complained at some point. Heegaard did not complain. That I've been very sloppy with categories. So I can phrase this question in the smooth category. I can phrase this question in the locally flat category. I can phrase this question in the PL category. And the answer really, really strongly depends on which category you work on. So what I'm doing here is assuming, I'm considering sort of the smooth. Implicitly, if there's no subscript, I'm thinking of smooth. I'm always thinking of smooth stuff in any case. So I want F to be smoothly embedded in order for this to be true, because the statement is false in the locally flat category. And you have a separate question, which is what is the minimal genus in the locally flat category? And in principle, you have a third question, which is what is the minimal genus in the PL category? So what is the minimal genus of PL embedded surface in CP2 representing a class of some degree D? And the answer is it's always 0. So it's very false in the PL category. And the example is actually algebraic. X d minus y d minus 1 z equals 0. This is a PL embedded, well, okay, it's isotopic to a PL embedded sphere in degree d, so in the homology class of FD. That it's a PL embedded sphere. So I'm not going to go in this direction because it's. No, this should be the same. The principle should be that whatever you can do for C1 holds for C infinity. The division is really between C0 and C1. But this might go back to theorems of Hirsch, or maybe even earlier. So I think that Hirsch's book on differential topology discusses these questions in some detail. But that's a very fair question. Good. So the goal is now to try and give a proof of that statement. Are we all on board? Good. Right. So what did we do so far? In this mini course, so far, we had started with Y, a rational homology 3-sphere, T, a spin C structure on this homology 3-sphere, and we had associated to it a magic number, the correction term, and to do so, we had used the fact that HF infinity of YT is just one single tower. So recall that this is just F U U inverse, and pictorially I have a tower where the lift only goes down, goes up indefinitely, down indefinitely, and the lift is the U action, multiplication by U, and the degree I plot up. And the question is, well, what did I really need in order to be able to define this number? I needed to have, well, I used the fact that I only have one tower here, but I could ask for something a bit less. I could ask, well, maybe I have more than one tower, maybe I have 16 towers, but is there a preferred one among all of these 16 towers? So is there a way to pick out, if I have more than one, is there a way to pick out one? And once I have a preferred one, then I can play the same game. I can look at the image of this tower, and I can look at the minimal degree in the image of this tower, and I can ask, well, is this a meaningful, this is going to be an invariant, and the question is this a meaningful invariant? Does it contain any information? Does it mimic in any way what we had for the properties that we had for the correction term that allowed us, for instance, yesterday, to prove Donaldson's theorem? And the answer is yes. Actually, there are two ways of going about this problem. So now, drop partially the assumption that B1 of Y is 0. So, word of caution, there are at least two ways of going about it. One way is to pass to fully twisted coefficients that I don't want to do. I'm going to get close to it, but I don't want to do it. And in that case, if you use fully twisted coefficients, for those in the know, if you use fully twisted coefficient, which is usually denoted with a bar underneath, then you really just have one tower. For every three manifold, for every torsion spin C structure, you have only one tower. No further assumptions required. So now you only have one tower, and you can define the correction term exactly as you did before. This was hinted at. I found out that it was hinted at in Orschwat and Szabo's paper in one of the paragraphs, just random remark. And nobody did it for maybe 10 years or so. And at some point, Stefan Behrens and I decided, yeah, okay, let's do it. And we played with it. But before that, Ojvat and Szabo played in a different direction. And there's also work of Lebin and Ruberman, Ruberman with one N, that do somewhat related things. So further work by Lebin Ruberman and by myself and Behrens from maybe 6, 7, 8 years ago, something like that. So how far do I want to partially drop? So I want to give a definition, and then I'll give a theorem. So YT, now Y is any three-manifold, compact, close-oriented, always the standard assumption, and T is a torsion spin C structure. We say that this has standard HF infinity if HF infinity of YT is isomorphic to a tower, well, not to one tower, but to 2 to the B1 of Y towers. Every time I add B1, I double the number of towers. And there's a theorem. Oh, no, let me do one example. We saw, or you saw, that for S2 cross S2, S1 cross S2, seeing that HF infinity of S1 times S2 in the unique torsion spin C structure, this is just the direct sum of two towers, one generated by one of the generators, the other one generated by the other generator, and there's no differential. This is the homology, not only the group, the chain complex. And so this has standard HF infinity because B1 of S1 cross S2 is 1, and we have 2 to the 1 towers. More generally, if you take a connected sum of H copies of S1 cross S2, then HF infinity of, let me call this YH for the moment. This is just the tensor product of H copies of HF infinity of S1 cross S2. And tensor products just multiplies the ranks, so we're fine. This is also standard. And the tensor product should be non-example, HF infinity of T3, again in the unique torsion spin C structure. This is isomorphic to 6 towers. So this is not standard. So not all three manifolds have standard HF infinity. This is actually a restricted property, which is one of the advantages of working with twisted coefficients. But yeah. So there's a theorem. I think it's just Lidman. Might be Lidman and Manorescu, I never remember. But YT has standard HF infinity if and only if the triple cup product of y vanishes. What do I mean by that? I mean that I have, I can take 3 classes in the first homology of y, alpha, beta, and gamma, and I can send them to h upper 3 of y by taking the Kappa integer h1 modulo torsion. As far as I know. Actually, this could work the way you're saying it. But don't, yeah, I haven't thought very deeply about this. I mean, you do have an action in that case. I'm not sure that the next proposition is going to be true, but probably yes. So maybe you're right. If you work with FP coefficients, I think you can do the... Yeah, definitely. Definitely. You still have a linear action. If you have a linear action over Z, you could definitely have a linear action over F2.
If I take 2 gamma, then
Yeah.
2 the answer is
Yeah.
0.
Yeah.
So the action on the effect,
Yeah.
usual effect with superposition should be.
Yeah, I mean, this is an action. Gamma plus gamma prime acts, if you let gamma plus gamma prime act, it's the same as acting with gamma prime, and adding the 2 results. So the fact that I wanted to state, which I should think about it if it's true over F2, but I'm not sure. I think it is that this induces an action of the whole exterior algebra on any HF. And fact number 2 is that HF infinity is standard if and only if isomorphic to a Taylor tensor the exterior algebra. As modules over this exterior algebra. Right. What is the advantage here? We have an exterior algebra. We have one preferred element in the exterior algebra, especially if we work over F2, we have the top generator. Or the bottom. Yes. Actually, the top is the bottom, but yeah. So confusingly enough, the top is the bottom. We'll see. So we have a preferred tower. Which I can view in 2 ways. It's either the tower, the one corresponding to lambda to the B1 of y of H1 of y torsion. You need to work over Z. You still have an action, but it's better to work over Z. Or equivalently is the one that's killed by all of H1 of y modulo torsion. Equivalent. I mean, if it's killed by all, it's also killed by 0. It's killed by all, including 0. And it's enough to test that it's killed by a basis. I mean, the top generator, the top dimensional group here is the one that's characterized by the property that if you wedge it with anything, it dies. And that's the same thing. And for degree reasons, since the H1 action decreases the degree, this tower that we pick out is the bottom tower. It's the one that morally is in the lowest degree. But the bottom line is that we pick out the single A tower, HF infinity of YT. So we can define the bottommost correction term of YT to be the minimum degree in the image of this bottommost that goes to H plus. Yeah.
Could you rewrite the word reverse to 1 sub A, which is actually more
The which one?
we have a Heegaard tower,
Yeah.
the arrow, and then there's the one.
One corresponding to. You're welcome. Yeah, thanks. My handwriting is horrible. Okay, so example, or exercise maybe, because I'm running late. The bottommost correction term of S1 cross S2 in its unique torsion spin C structure is minus 1. And now, what you would hope is true actually turns out to be sort of true. So yesterday we had this inequality. So if W is a negative definite cobordism, my shorthand is negative definite cobordism between rational homology 3 spheres, then we had an inequality on correction terms. B of YT plus C1 square of S. Yeah?
Dr. Yes, are we still using that it's a torsion species structure somewhere?
Yeah. Because if it's not torsion, you have towers. And you don't have an integer degree.
So we're still assuming this?
You don't have it right.
Once CS1 plus 2, then it needs to be
In the unique torsion spin C structure. Yeah, maybe I should still write. So this we had for rational homology spheres. So this is from yesterday. Today, the theorem is upgraded and downgraded at the same time. But if Z is negative semi-definite, I'm going to say what this is in a second, and this is what the French would call negative definite. With boundary of W for Y, and Y with standard HF infinity, and we learned from Diego's question that we actually don't need to worry about which spin C structure we're talking about. Is if one is standard, then all of them are. Then the bottommost correction term of Y plus 1/2 B1 of Y is at least C1 square of S plus B2 minus of W divided by 4. So this is the same inequality that I had here.
What is C1 squared of S? And then what's written there? Plus or minus? Plus?
This is B plus
Up
B2
there.
minus
Yeah, plus
plus B2 of W.
B2 of
W. And this is Z.
B1 0. This
No. No. I'm not assuming that B1 is 0. In the proof, I can reduce to the case where B1 is 0, but I don't need that. And here, actually, I do need B1 0. Sorry. Here in the second statement, I think I need B1 0. Let's say H1 is 0. But B1 is 0. Sorry. W is Z, yes. I would expect Patricia to make this remark, but so just to be on the same page, negative semi-definite means that there are no classes of positive self-intersection. English positive, not French positive. And when I say B2 minus of Z, I can think about it in many, many different ways. I can tensor it over R, diagonalize it over R, and count the number of minus ones, or well, yeah, of minus one in the Sylvester's inertia theorem. Or I can think about it as the maximal number of pairwise disjoint surfaces of strictly negative self-intersection that I can embed in Z. These are equivalent definitions. And this is the bottommost correction term of S restricted to Y. So this is the spin C structure of S, and I'm restricting it onto the boundary. Yep. I think that in this case, things are a bit more delicate. You can replace it with a different assumption, but you cannot just say it for any. I think you need that assumption. And the example that I think you want to have in mind might be D2 times S2. No, sorry, S1 times D3. I think that's the example that you want to have in mind.
Y has B1 doesn't somehow doesn't also Z likes to have B1?
No, S1 times D2.
Yeah, of course, but I mean, it might like to have some.
Yeah, but you don't need to. I'm stating as an assumption that you don't have B. I'm stipulating that. So this is pulled out of thin air, but the proof is the same as the proof that I didn't tell you about yesterday, or roughly the same. So if I didn't tell you anything about yesterday's proof, I'm not going to tell you anything about today's proof. Well, or rather, I told you something by black boxing the statement that I raised about negative definite cobordisms. The proof is the same. You just have to box out an analogous statement. Not exactly the same, but an analogous statement for negative semi-definite cobordisms. Right. So back to the question that, of course, I just erased. But how do we use to prove? How do we use this? So let me try and give an overview of how to prove the Thom conjecture using these tools. Okay, so you have your CP2, and you have some surface lying around in some homology class. Smoothly embedded. And you want that the homology class is fixed, and this is d times h, which recall is just d times the homology class of the line. And, well, you want to produce a four-manifold with boundary out of this. You want to produce, ideally, a four-manifold whose boundary you understand sufficiently well. And you want to produce a four-manifold that ideally satisfies these properties. You have a hammer, you have a nail, there's not that much you can do. So what do? The one thing that I like to do a lot, you remove a tubular neighborhood of F. And we remove a tubular neighborhood of F, you get the complement of F. So I want to view CP2 as the union of a neighborhood of F. Closed tubular neighborhood of F, union along its boundary with W, which is just the complement, the exterior of the complement. So the complement of the interior of N. And maybe I should call this. You know what, I'll stick to W because I know that I will turn to W at some point. So imagine that there are W's there. Claim is that we understand completely the algebraic topology of W. And let me also call G the genus of F. So the claim is that the homology of W, this is Z in dimension 0 or degree 0. This is Z mod dz in dimension 1. And this is Z to the 2G in dimension 2 and 0 otherwise. So it's a four-manifold that has B1 equals. It has a rather large of this gadget. So the second claim is that the intersection form is null. Not the zero vector space. This is not the zero vector space. It's not the zero lattice. But it's a lattice with zero intersection form. The product between any two elements is 0. The square of any element is 0. There are no surfaces. This is equivalent to saying that there are no surfaces of non-zero self-intersection in W. Actually, you can describe very explicitly the surfaces, well, the set of surfaces that generates H2 of W. For those who know, these are called rim tori. And they're just tori that lie very close to the surface. So, good news is that at the very least, W is a good candidate to which we can apply our theorem. It has no surface of positive intersection, so it's negative semi-definite. And it has B1 equals 0. We don't exactly know what its boundary is yet, but that's the next step. So the boundary of W, this is an S1 bundle over F of genus of with the Euler number equal to minus d squared. I can give a somewhat concrete handle description, or actually I can give a handle description of n, and I can give a handle, well, a surgery description of this boundary that, of course, since it's three-manifold, I'm going to call y. This is a pretty explicit, so very explicitly. Let's view it from the n perspective, so from the neighborhood perspective. The neighborhood of the surface is a thickening of F. So it has a handle decomposition with one handle for every handle of some handle decomposition of F, and with the same index. So it has a handle decomposition with 1, 0 handle, 2G, 1 handles, and 1, 2 handle, which is attached along a single null homologous knot in the boundary of the one handle body. So I can view, well, actually I can view n is equal to the boundary connected sum of 2G copies of S1 cross D3. This is what I obtain up to adding the 1 handles. Union a 2 handle, which is attached along the so-called Borromean knot, or the genus G Borromean knot, with framing minus d squared. And I'm not going to describe exactly what the Borromean knot is. I could. It's relatively easy to see what it is. I just want to convince you that the 2 handle has to be attached along a null homologous knot. And this is because otherwise I would have no H2. And if I want some H2, I better have that my 2 cell is attached to something null homologous. Otherwise, I kill some class in H1. And the framing has to be plus d squared, because the framing of the attachment of the 2 handle is the self-intersection of the generator of the second homology of n. And the self-intersection of the second homology of n, well, since F is in the homology class DH, and, well, I haven't told you, because when I defined CP2, I should have also said that Q of CP2 is equal to plus 1. So if I have D times the generator, its self-intersection is D squared, the self-intersection of the generator, and the self-intersection of the generator is 1. So the self-intersection of F is D squared, and so we get D squared. Yep? Because I, so the boundary of n is not canonically oriented. If you orient it as the boundary of n, you get Euler number plus d squared. If you orient it as the boundary of the complement, you get the opposite orientation, so you get the minus d squared. Orientations are a nightmare. I spend half of my life fighting with orientation, just as much as Emmanuel spends half of his life fighting with science. So maybe more than half. The claim, well, maybe this you can even, maybe I can even prove this. But the claim is that y, so this y, has trivial triple cup product. Or equivalent, it has standard HF.
So n. Y is n.
No, y is y. Y is the boundary of n, or the boundary of W.
Oh, I'm sorry.
So convention, y has 3 n's when you write it, so it's a 3 manifold. X has 4 n's, so it's a 4 manifold. And if you call it something else, nah, you get me confused. Right. And okay, I think this is all we need for the topology. We go on to the Floer homology side. Well, I just claimed that this is standard HF infinity. I can actually prove it for certain spin C structures without having to know anything about triple cut products. But on the Floer homology side, I can prove that for some spin C structures, and I can be more precise, and I will be perhaps more precise, when D is, let's say, when D is sufficiently large with respect to the genus, then HF plus of Y, let's say T, is isomorphic to HF plus of S1 cross S2 in the standard spin C structure up to a shift. A shift in degree. Y, that's a good remark. Y, so H1 of Y is Z to the 2G plus Z mod D squared Z. Mod D squared Z. So it has D squared torsion spin C structures. So up to a shift, these two are isomorphic. So if I understand the shift, I understand, and this is actually as, so the exterior algebra of, so this is a lambda star H1 of Y, sorry. This is a connected sum of 2G copies. This is a lambda H1 mod torsion module. And this is abstractly lambda star of Z to the 2G. And this is also a lambda star H1 of 2G copies of S1 cross S2 module. And this is abstractly the same as lambda star to the 2G. But actually, since Y is a surgery along a null homologous knot in a connected sum of copies of S1 cross S2, I can identify these two modules. And when I identify these two modules, actually this isomorphism is still up to a shift, an isomorphism of lambda star Z to the 2G modules. What does it mean? Concretely, it means that this isomorphism takes the bottom tower in any spin C structure here to the bottom tower in the trivial spin C structure here. So if I want to compute the bottommost correction term of Y, I just need to compute the bottommost correction term of this connected sum. And this is easy. This you can do using essentially the example up there and taking connected sum of the surface. There's nothing mysterious, nothing magic. This has bottommost correction term, which is minus G. Yeah?
You said that every species starts from Y, but again, we want every torsion species.
Where did I say every species structure?
No, before.
Yeah, yeah, this is for torsion. For some torsion species structures.
What D is the degree of the pattern.
Yeah.
But in
No. D squared is the degree of the bundle.
okay. But it's still there's a relation between D and G. You can't really say.
But that's what we want to prove. I mean, we want to prove that the degree bounds the genus.
Yes, but you won't do that with the generic statement for D is sufficiently larger than C.
No, you can say exactly for which Ds and for which species structures and for which Gs. Yeah, I'm being vague. This is an overview of the proof that I will not give at this point, but I wanted to give an overview. And I'll tell you what I need at some point.
Can you just say this you can answer this isomorphism?
Can identify. You can identify these two algebras.
Are you not saying that the bottom of Y is also a G?
No, because this is up to a shift in degree.
Okay, but you don't know it.
I don't know yet,
And it's
so
minus U and G. It's minus.
this is minus G. So the next sentence that I was going to say is exactly that if you want to compute the bottommost correction term here, all you need is knowing the bottommost correction term here, and we know it, and the shift. And the reason that you can compute these things is that we know exactly where this isomorphism comes from. This is not just you compute the thing on the left-hand side, you compute the thing on the right-hand side, and the two agree. This is rather unsatisfactory isomorphism. So, but there's, so the isomorphism comes from a modified surgery exact triangle so the exact triangle that Paolo told you about links the infinity surgery, the zero surgery, and the one surgery on a given knot, in null homologous knot in some three manifold. There's a variant that connects the infinity surgery, the zero surgery, and the p surgery for any positive p, or maybe the one that we need now is 0 minus p0 for any p positive. It's not exactly the same species, the same triangle. Actually, there are, I think, p surgery triangles here and p surgery triangle here, and we're using some of them. But yeah. So this isomorphism comes from looking at the surgery exact sequence, the surgery triangle, in some appropriate species structures. So let me write down at least the three manifolds that appear here. This is T0, this is T, and this is HF plus of S1 times F. I'm going to write this, actually maybe I should write the sum over a certain subset of species structures. But of torsion species structures, and this subset, I mean the set of torsion species structures here, no, not torsion, of species structures. The species structures that are concerned are just a copy of Z. They correspond morally to multiples of the surface, morally, or multiples of this. And this certain subset, it's an affine translate of d squared z inside z. So this is more. I'm not going to give more details, but we understand exactly which spin C structures appear here, given a spin C structure here. This is getting more and more vague as time goes by, but there's a theorem by Oshpat and Szabo. So computing the Floer homology of all three gadgets in there is hard. It has been computed for the product of a circle with a surface, but it's a mess. But the only thing that we know is some vanishing result. Name HF plus of S1 times F T vanishes whenever C1 of T evaluated on F, or technically point times F, which is a subsurface in here, is larger than 2G minus strictly larger. So there's a compact region of non-vanishing for these groups. Nope. This is for C non-torsion. This is a general statement about vanishing or non-vanishing of Floer homology groups. Here, note, so T on Y, I want it to be torsion, but the T's that I have on S1 cross F need not be torsion. Actually, on S1 cross F, you only have one torsion spin C structure because you have no torsion in H1. So let me glue the pieces together for 1 second. So what I'm saying is, well, I understand. So this group is fixed. The bottom group is fixed. The leftmost group is fixed. And the thing that's changing is the P or the D. So it's the index of the surgery we're doing. If the index is sufficiently large, then among all of these triangles that I have, all of these variants of the triangles that I have, most of them involve a trivial group. This group will be trivial. Maybe let me say T prime here. For most choices of T, the spin C structure on Y, if D is sufficiently large with respect to the genes. And as Paolo complains, and rightfully complains, that I should say what I mean by sufficiently large, but I don't have time to go in complete detail. And if this vanishes, then we have an isomorphism between the two groups up there, because it's a surgery exact triangle. So for most spin C structures on T, we have an isomorphism as I claimed. And that map up there is the map induced by the surgery cobordism. So we understand the algebraic topology of the surgery cobordism. We understand degrees of maps. And we can actually compute the degree shift that we need. This is not so far from what we've seen on Monday and what we've seen yesterday. It's just that we're dealing with things that are not rational homology spheres, and things get a bit messier. What's the bottom line? The bottom line, yep. Yeah.
And you're saying that we can choose a good surgery coefficient, so we have a
If the surgery coefficient is sufficiently large, there's a subset of spin C structures on Y for which the group at the bottom, the corresponding group of the groups at the bottom all vanish. But for every choice, for each choice of the framing, there are some bad spin-C structures. So choosing which ones are good and which ones are bad boils down to understanding this claim. Right, so let's try and make things slightly more concrete. The degree shift I can compute. By what I just said, it's really just computing squares of first-term classes in a cobordism that is just a 1-2 handle attachment. This is something extremely concrete with respect to everything else that I've said. And we can compute at the bottommost correction term of y on t to g. I'm going to say what t to g is in a second, is 1/4 minus g squared divided by n minus n divided by g squared. And the spin-C structure to G is the restriction of the spin-C structure S2G. This is on the surgery cobordism from this connected sum of 2G copies of S1 cross S2 to y d squared, where S2G, its first Chern class, evaluates on the generator of H2 of this surgery cobordism, which I call W surge. Well, technically the relative one, but let me not go into details, as d squared minus 2g. Okay, great. We're almost there. It doesn't look like it, but we're almost there. So what's the idea? The idea is, suppose the genus of f is strictly smaller than the genus of the Fermat curve. And actually, up to adding trivial handles, I can assume that I'm sort of at the worst possible case. So I'm just genus that I want. Then construct W. We did before by removing a neighborhood. And now we have all the ingredients that we want to compute here. The genus we fixed. This is just 1/2 dd minus 3. So we have all the ingredients in this formula. And now we want to apply the inequality that luckily is still on the board, and we want to ask, does this hold or not? So we can compute d bottom of y in this spin-C structure here. In the W, I said surgery, it's surge. For surgery. Have all the ingredients. So choose the spin-C structure on no, it's W surge. It's more or less, it's the neighborhood of the surface minus the one skeleton of the surface. So choose, sorry. CP2, so that C1 of S evaluated on H is -3. And if you're an algebraic geometer, or if you know complex surfaces, you recognize that this is the canonical spin C structure on the one corresponding to the canonical bundle. So the D bottom of Y in the restriction of Sy, you can check using all that I said, that this is the same as S to G or T to G. Plus 2b1 of Y, this has to be at least 0. But now we can, we have the computation for D bottom. So this is 1/4 minus G squared divided by D squared minus D squared over 4 plus twice b1 of Y. And thanks to Gregor's question, we know that H1 of Y has free part of rank 2G. So B1 is 2G. So this is G. Sorry, this is half. I cannot even copy my own inequalities. Plus G. This has to be at least 0. But if you use this formula, this actually turns out to be -1. This is just a computation. And so this gives a contradiction. And this proves it here. And maybe in the last -3 minutes that I have, I want to recap what has happened, because this is a lot to take in, and I've black boxed a few things. So what happened is, I want to prove that the genus of F is at least the genus of a complex curve. Suppose it isn't. Up to adding handles, I can suppose that I'm as close to the minimal genus, or to the supposed minimal genus as I can. So that I'm really just one away from the minimal genus that I want to prove. I have one spin C structure. I have one preferred spin C structure on CP2. This is the canonical spin C structure, the one that comes from algebraic geometry. And I'm taking that spin C structure and I'm restricting it to all of the pieces that I see. I have 3 pieces. I have 4 objects that I'm playing around with. One is CP2. One is the neighborhood of the surface, tubular neighborhood. And one is the complement of the neighborhood. And I'm restricting this spin C structure on all 3 components. The restriction on the first component, so on N, allows me to pick out one spin C structure on Y. And for this spin C structure, somewhat miraculously, this exact triangle of surgery coefficients tells me, oh, lo and behold, this group vanishes. This is a bit of a miracle, but it pops out of the computations. It pops out of the computations because the spin C structures that are involved here are all spin C structures for which this lemma applies, so the corresponding group vanishes. And I understand the map that gives me the isomorphism between these 2 groups, so I can compute explicitly the degree shift, and so I can compute the bottommost correction term of that 3 manifold in that spin C structure. And also, I understand perfectly well the topology of the complement. And the topology of the complement says, oh, I can apply the inequality just I have on the board. And when I apply this, magically, I can compute everything. This is a miracle. It's already a miracle. And not only can I compute everything, but also what I compute gives me a contradiction. So it shows that the genus cannot be smaller than the genus that I wanted. And so it implies that such an F cannot exist. So this is a very bird's eye view of the proof, but it's somehow how all the pieces in this proof fit together. And I think I should